I'm in comfortable territory here in Windows. Okay, happy. Great. So we're going to have, we're going to have this progress. So we're going to have them progress amongst these states. Can we talk about this? You'll notice that this transition, if you go click on it, you have a variety of choices. With transitions, there's basically about 4 major types of transitions. There are timeout transitions, denoted here with this kind of clock. See that? I'm going to move this up so we can expand this a little bit. Okay. There are rate transitions, which are going according to some hazard rate, which may be changing over time. So it's some chance per unit time of going. So it's a memoryless process at a given point. If it's a fixed value for that hazard rate, it's a memoryless process. They have a certain kick at the can every year, but it's in continuous time. So their time in this state is exponentially distributed for those who are comfortable. The residence time is exponentially distributed. It's a memoryless transition process. Those words may be familiar to some of you, but not to others, but that's what's going on. Alternatively, you can have a condition. They transition here based on some condition in the model, based on a message. We're going to see that this afternoon, or based on their arrival at some destination. In this case, we're going to make it a rate. Okay? No, this is continuous time by default, so it's a hazard rate. It's a chance per unit time. Now, you can actually, any logic does support probability as in discrete steps, time 0, time 1, time 2. You can do that. There's actually this notion of a model step, and you can use that instead. But in general, it's very handy, having done a lot of both, it's very, very handy to use continuous time rates. Because think about a situation like this. Imagine that this person is subjected to competing risks, right? They're subjected to risks associated with gaining weight and risks perhaps associated with dying, with mortality. Now you've got this competing process, and if you do things at fixed intervals only, time 0, time 1, time 2, which is the traditional way of doing things in NetLogo, for example, a traditional way of doing it in Repest, although now it's been expanded to include continuous time. Then you've got to kind of figure out, okay, time 1, which of these things occurred first, conceptually? Sort of, which occurred before the other? Here it's automatically brokered. You can have multiple transitions. Whichever occurs the first point in time happens as the one that goes first. So maybe they die before they gain weight, or gain weight before they die, and it's much easier to deal with. You don't have to kind of manually broker which occurred first at these time boundaries. Instead, these are in continuous time. At any point during the year, someone could gain weight. And as a result of that, because we're doing things in continuous time, what you're dealing with at a technical level is not probabilities, but probability densities. You're dealing with a chance per unit time, not a probability, but a probability per unit time. And what you have is a stochastic process in continuous time, where basically I have a hazard rate, would be another way to put it, a certain chance per unit time. And that hazard rate can change over time, but if we have a fixed hazard, what we have is a classic sort of memoryless process from this to this, which I've not a kick at a can once a year to go, but instead at any point during this year I could go and gain weight. So it's actually handling that for me. It's very useful because if you have a very rapid rate, you'll go in 1/10 of a year. If it's a very slow rate, you may go in 10 years, but it's in continuous time. Is that helpful? Or does anyone else want to talk about that a bit? Let me ask this. This is actually a very useful thing. So suppose we had a rate of 0.1 per year. You'll notice it lets you pick here and because it was per second. Look at that, Dylan. It still did per second. Make sure it's per year, 0.1 per year. How long would that mean we're on average? Suppose that we're fixed right now. We're going to have it changing by age, but suppose that we're fixed. how long would they spend in average in that normal and overweight state? If it was 0.1 per year, on average, they'd be spending, does anyone know the theory of hazards when you have a hazard rate like that? You have a chance per year of leaving of 0.1. The average residence time is the reciprocal of that. It's 1 over that. So the average time will be 1 year in that state. And I have lectures online where that's derived. It's the same thing, by the way, with system dynamics flows. If you have a certain chance per unit time of leaving down that flow, it's a memoryless process, and your average time in that stock is 1 over that rate if there's no other competing flows. So a rate of 0.1, your time in that stock, it's exponentially distributed, so you're going to be your chance of remaining in that stock is going to be declining. Not like that. It doesn't go to 0. Forgive my poor drawing of this. It's e to the minus, in this case, 0.1 times time measured in years. Your chance of remaining there, this is continuous time here. Yeah, and this is the probability of remain in this normal and underweight stock. This is what we call a hazard rate. Your hazard rate stays the same. You have the same chance of 0.1 per year, but it's in continuous time, so you have this hazard that you could leave at any point during the year. Is that? Probably don't have time to cover it in more detail than that, but there's a very well-developed theory of hazards that's used. I mean, it's not to do with any logic. I mean, it's bread and butter for survival analysis and for continuous time survival analysis and other domains where you're dealing with probability densities. Is that okay? Okay. Alternatively, we could use a timeout where they go after exactly some amount of time. This is memoryless. This is saying their chance of going in the next year is independent of how long they've been in that state. Wow. My chance of developing, overweight is independent of how long you've had normal and underweight. If I just have a fixed hazard. Okay, great. So we have this, and this other type though is still a timeout, as indicated by this. We could make it a rate. Let's make it a rate, and let's make it 0.2. Okay, from overweight to obese. How long on average would someone be spending overweight before becoming obese then? 5 years on average. Yeah. Good. Some more, some less, but on average 5 years. Okay, so stochastic process. It's actually drawing, secretly, beyond what's going on there. It's drawing from an exponential distribution, that one shown there. Okay, great. And then you got to check. Oh, gosh. Because we had this model initially with a time unit of seconds, we've got to say per year. Yeah. Okay. This is great. So, ladies and gentlemen, can we run this model? Run or not? Run. Okay. Thank you. So let's run it. Right click here. And we're going to see those people grow. Look at them. Okay. I'm going to pause this model. You notice I've run this out. Well, let's run it out a little bit more. You can speed up the runs by pressing that thing there. And I've run out to 36 years. I'm going to go now browse the population. I'm going to dive down and look at each population member. Here's a population member who is what? What do you think that red circle means? They're currently obese. Okay. Oh wow, we have a very high rate of obesity indeed. This is sobering. Okay, but if we had stopped the model earlier, let's say stop it after 5 years. Okay, boom. Okay. Hey, oh man. Well, I tried. Let's try that again. Okay, here we go. Okay. No, that's 11 years. Okay, that will do. Here's someone who's normal and overweight, normal and underweight. This one's obese. This one's obese. So they're transitioning. You notice that it puts actually an indicator here, 3.121. What that's saying is in 3 more years, by default, if nothing else has happened to this agent, 3.121 years or they'll be going to an overweight state. It's kind of predetermined. It's drawn from that exponential distribution for when they'd be leaving. So here we have the state charts. Okay, so here's the state chart. This person's currently overweight, and in 6 more years they'll go here. Ladies and gentlemen, a few pointers on running the model, and I should probably nuggetize this component.